you for inviting me to have this opportunity. So I am at the Kavli Institute for Particle Astrophysics and Cosmology, or KIPAC, and I would like to tell you today about how we use high-performance computing to help solve some of the current mysteries of the universe. There's a lot of research that goes on at, that's okay, yeah, that goes on at KIPAC, and but I'm going to focus today on cosmology, in particular the large-scale structure of the universe and what we're doing there. It's okay. As long as I was just trying to use the laser pointer. That's fine. Yeah. All right. Anyhow. All right. So I'd like to tell you about large-scale structure and how we use high-performance computing. So let me give you a little primer on our research. So first of all, just to give you the big picture, the observable universe is a sphere roughly 90 billion light years across with us at the center. At least that's how we look at it. Obviously, that's the observable universe, so we're at the center. The diagram here on the left shows you a sort of schematic view from outside, as you would think about it, where the left is the beginning and the expansion goes towards the right, and you have structure forming. So these are kind of two views. This is the one on the right is the observer's view. The one on the left maybe is more the theoretical view. So the further away we look, the further back in time, and so there's naturally a finite extent to which we can observe, which is defined by the initial time, or where the Big Bang happened. And so that defines that 90 billion years across, and you might wonder, well, why is that not something more like 2 times 14 billion, which is the age, and that's because of the expansion of the universe and the way we measure distances and so on, but let's not get bogged down in that. So if you look down at the bottom there, you see that sphere we were looking at, and the surface is what's called the cosmic microwave background, which is currently the earliest we can see, which is a few 100,000 years after the Big Bang. And in the early 90s, variations in this radiation were detected and have been subsequently studied in greater and greater detail. And basically, they're like the baby picture of the universe and tell us about the initial conditions, and have been received a Nobel Prize for this several years ago for its detection. Now, when we talk about the outstanding, really big questions in cosmology, one of them is about cosmic inflation. It was developed several decades ago now as an idea for what set the initial conditions for the Big Bang. However, the connection to fundamental physics is still unknown. To the extent that you can even think of it this way, it would be that the entire universe would be smaller than a nucleus and then expanded to about a meter in a tiny fraction of a second, at least on paper. I mean, I don't know what any of this actually means to our brains, but that's the actual idea. And then from then on, it's after that, it's what we call the hot Big Bang phase, which we understand better, especially a few minutes after that, and things really start to hang together in terms of the nucleosynthesis of light elements and so on. Anyhow, one of the key predictions of inflationary theory is the generation of quantum fluctuations that would eventually become the large-scale structure that we see today and is responsible for the formation of galaxies, planets, so on, through gravitational collapse. So it's really a linchpin of our entire understanding of the universe. Not been, still controversial to some extent that inflation is the correct theory. So this is why I'm telling you about it, because it's a really big, interesting question. So going back to this picture where we're at the center, all those dots there are galaxies. And so by looking at the overall pattern of galaxies, you can map out the large-scale structure of the universe. By looking at distant objects for which you can know the intrinsic luminosity, you can tell their distance. other ways of knowing the distance by looking at the pattern of these fluctuations and comparing it to that cosmic microwave background fluctuations I showed earlier, allow you to have a sort of measuring stick which can measure the expansion of the universe. And very surprisingly, discovered maybe 20 years ago now, is the fact that, and you can kind of see it in the left there, the way it starts, that inflection of the diagram, that the universe expansion is actually accelerating, which is not what you would expect because gravity is an attractive force. So you would not expect the expansion to begin to accelerate, but that's what was seen. So that is the second mystery. Big open question is dark energy. So these are the two that I framed for you here. And these are really, I would say, like the big ones in cosmology that are driving the field forward. To start to get a little bit more quantitative, the standard model is called lambda CDM, lambda for the cosmological constant, which would be a version of dark energy. That would be a constant that would cause the acceleration. CDM for cold dark matter. That's a separate topic I won't get into today, but that's what we call the standard model, lambda CDM. So this is a baseline. And you know, it has, I've listed 6 parameters here. These are the big ones. There's a few more. I won't go through them all in any kind of detail, but it's just to say that that's sort of where you start. You add that, and then during inflation, the fluctuations are essentially random. So you can just think of them as white noise. And then using these parameters, the choices we have, numerical choices for each of those parameters, sets the correlations in those initial conditions and the overall expansion rate, and that's basically it. So that's your model. Inflation, and you see those 2 numbers there, F sub NL and W, are additional parameters that would allow us to probe at different kinds of inflation. So F and L is the amount of non-Gaussianity in the initial conditions, so not just white noise, but perhaps some kinds of correlations that are there from the exotic physics that we think about during inflation. And W is the so-called equation of state parameter, which for a cosmological constant, or lambda W, would be equal to -1 and would be constant with respect to time. But it may vary, and you'll see more about that later. So data holds the key. These are all observatories and surveys that KIPAC is active in, both theoretically and also through Stanford and SLAC, other physics and departments in SLAC in terms of the camera for the Rubin Observatory and the data operations. So that's just to say that we have currently ramping up large observations, surveys of large-scale structure that should tell us about this. One that I worked on quite a bit in the last few years is the dark energy spectroscopic instrument, so I want to take you a little bit through that. Really interesting instrument mounted on a telescope at Kitt Peak, southwest of Tucson, the Mile telescope. And basically these the top right there, you see all those little dots there are actually fibers. There's 5,000 of them, and there's a fiber optic cable that comes from each one. And they're on these little robotic arms that can move around. So each time it points at the sky, there's a pre-targeted list of galaxies that each little robot moves to. And then the light goes through that cable and is fed into a spectrograph, which is then dispersed, and you get the spectrum, which you can see in that bottom right there. And that's kind of, I like this diagram there on the right, which shows a picture of the Andromeda galaxy, M31, our nearest neighbor, that was taken. And so you see that 3-degree field of view, which is, so you just imagine instead of a CCD, you just imagine 5,000 fibers on the focal plane, each one taking a galaxy. So there you see some quasar, which is a accreting black hole in the distant universe there, and the spectrum that it can take. So this was dark energy spectroscopic instrument was designed to map out the universe by doing this. And this is when I was working on the spectroscopic pipeline. This was an animation I made back in when operations started. And you see on the right there the 2021, you see October, you see each day. And so each night it slews and it looks for a few minutes at a given portion of the sky, and then it goes back and forth, and that's what you see doing there over time. And those number there is for each one of these tiles is how many objects, so of order a few thousand. You see those numbers kind of add up to 5,000 for those 5,000 fibers. There are other fibers doing other things like looking at the sky or stars to calibrate. And so that's how sort of painstakingly, night after night, this map has been built up. And so I wanted to show you this because DESI has been in the news recently. And so I'll just let this kind of go. So here are the number of galaxies. I was getting up to 4 million at that time. And by now, after a few more years, it's up to, I think, 16 million galaxies that have been mapped out, roughly halfway across. Well, maybe a third of the way across that observable universe. In this animation and in the other animation, you will see a region that's not mapped, which is called the zone of avoidance, which is where our galaxy is. And we just can't. We'll never map, well, never say never, but we'll probably never be able to map out the universe in the galaxy because it's too much stuff in the way. And this is now the sort of press release version of this after 3 years of observations. So this is map of the universe. And it's the largest map ever made. This is kind of what you would see at a planetarium when they zoom out and show you all the structure. So really cool stuff, lots of galaxies. You see this pattern, this filamentary pattern with these walls, filaments, sheets. That's the typical large-scale structure pattern, and that's what we look at to try to understand inflation. And also, these objects trace out the expansion history of the dark energy, as I was telling you earlier, hence why it's called the Dark Energy Spectroscopic Instrument. So it made a big splash a few weeks ago. Let me just show you this. So remember that number W I was telling you about, that if it was -1, that's W not in this diagram. That would be the cosmological constant up there, and these are contours over what DESI has measured. So not just pretty pictures or just making maps just to make them, although that by itself would probably warrant trying to make these maps, but real quantitative analysis. And now I start to get into the computations and something more relevant to what you guys are thinking about here. But the basic idea here is that, not to bury the lead, right, that it's starting to say that it's not looking like a cosmological constant. It's still tentative, but the dark energy doesn't seem to just permeate space and stay there neatly. I emphasize the tentative. So this, this lambda thing that you may have heard, like, Einstein's greatest blunder when he tried to make the universe static by just keeping it from collapsing, this lambda term. Maybe it's not actually the case, and so that will point to other kinds of origins for dark energy. So yeah, that was just the sort of deep dive into DESI, which has been in the news and is one of the big data sets that we've been looking at. Now to simulations. So again, just to orient you, this is what we're trying to look at. And it probably doesn't need too much convincing to imagine that simulations would be helpful here, because it's super complicated, actually. You start with that noise, but gravity amplifies it, creates these large-scale structures. Each of those 15 million points is in itself a galaxy, which has formed stars and so on. And you need to understand how those galaxies form to some extent in order to be able to create these maps. So what I'm showing here, and these are from simulations done at KaiPAC by colleagues Tom Abel, a professor here, and Risa Wexler, along with Ralph Kaler, who's a visualization expert. Oops. And what I want to show you here is this dichotomy in large-scale structure theory between dark matter on the right, which only interacts gravitationally and is easier to model because it's just a bunch of points interacting over 1/r² forces, attractive forces, and on the left, galaxy formation. So you see galaxies here. You see dust lanes. Over time, gravity amplifies those perturbations that were present earlier, forming lumps that are galaxies that then interact with each other. And so understanding large-scale structure is a matter of how do we go from those simple white noise type initial conditions with simple correlations to this complicated structure and then decode it back out to tell us about the universe. So just to start putting some numbers, if I take that volume that we're typically looking at in these big surveys, GPC is a gigaparsec, so a billion parsecs across. Parsec's about 3 light years. So you take that volume, and then you take the typical scales that need to be resolved in order to form galaxies. You have about 200 kiloparsecs, or 0.2 megaparsecs. And so naively, if you just wanted to do a simulation where you just looked at the dark matter and just formed all the galaxies, you'd need about 65,000 cube resolution elements, or with 4-byte floats. The initial conditions alone would be 1 petabyte. So typically the way these runs is you give it a random seed and you generate it forward, so you only need the seed in some deterministic random number generator. But that's for a random universe. But then, of course, we actually have our universe. So what we really want to do is the goal is be able to generate a sort of digital twin of our own universe with all our theories on it that we actually modeled on the computer. And so then numbers like that for the initial conditions actually start to become kind of relevant in terms of what you might actually need on disk. Now, this is just one example of a run we've done. We're mounting a simulation campaign that generates these sort of mock catalogs, basically to allow these surveys to do simulated observations to validate their pipelines. We've done, this is just to give you some idea of some scalings that we've done recently, strong scalings for these runs, really pointing us towards a small number of nodes as being the most efficient. A strong scaling in these units would just be horizontal. So, and this is using a code that runs on GPU, and which we're in the process of porting to the machine here, Marlo, which has been a nice experience so far. These scalings were done on the Perlmutter machine at NERSC on the other side of the bay. So let me continue here. These are the scalings we came up with. And the largest run we want to do is about 7,000 cube resolution elements. And we anticipate it should take about 20,000 GPU hours, which is a lot of GPU hours. But as I was saying earlier, it's only for one realization. And furthermore, those parameters I showed you, it's just for one set of those parameters. We want to be in the situation where we can vary the parameters and keep on doing it. So it's starting to get difficult. And then, so stopping there for a moment, that's what you would need to do for one. Now we have this other campaign that was recently finished, simulations in December on Sherlock, the machine here. I came here, I'm actually new. I came about a year ago and started using Sherlock, and it's been a really wonderful experience. I can't say enough about for sort of campus cluster how smooth things typically go. KaiPack has invested some resources into buy-in on it, and so it's just been a great machine for us. And you could see from that animation I showed earlier that you need sort of, you would need to have a multi-scale approach to this. You can't just do one simulation, so you kind of have to do one smaller scale and build up your knowledge. And obviously, surrogate modeling, machine learning kind of approaches are going to be very important. So this was the campaign, about 4 million CPU hours data, about a petabyte that's coming out. So what happens with these simulations is you start with some random seed. They generate a lot of data, but then you want to compress it back down into like these points that you would see. 15 million galaxies is not that much data, right? But what produces that data is a lot more, and it gets condensed back down, and hopefully eventually condensed back down to those few parameters, things like W. So it's this kind of like start small, go out, then come back in. And how long do you need to store all that data? We're currently hosting this data and starting to mine this data set. This is now approaching the resolution we need, but surveying different cosmological parameters, now moving beyond just the one set. Excuse me. So the idea is that we have these sort of, we call it an emulator that does these smaller regions, but high resolution, and then puts galaxy formation theories in it, makes the mock observation of the universe, and then out can come mock observations for different cosmological parameters, and hopefully for different realizations of the initial conditions, so we can start to do differentiable modeling, where we iterate and start to build up an actual view of our universe. So let's see. So have a little time here just to say a little bit more. This is the last slide. So IO-intensive simulations will be very important. So this 25 simulations and about a petabyte of snapshot data is sort of where we are now. But in the future, what we want to be doing is to automate this process. And the reason this data is just sitting on disk right now is because we could not, you might say, well, we just want to be able to run it streaming and do all the analysis at once. The problem is that you're constantly iterating the models and learning. So even for a fixed simulation, you don't want to just throw that data away or have to go through burn another million CPU cycles just to generate it again. So you need to keep it, excuse me. But the idea here is that you want to be at a place where these models have compressed the information enough that they can be done on the fly. But I don't think that's really happening anytime soon. So we're going to be pushing constantly, always pushing for more data as much as we can, more storage as much as we can get, I think, for the foreseeable future. It's not going to be where you just have some AI that comes in and makes the map for us. And I mean, we want to do that, but we're not quite there yet. And for the time being, we are going to have this multi-scale approach where we have to generate this large amount of data and keep it. So that's on the computational side. Very exciting is the new survey data. I want to highlight Rubin. That's big news here. It's in Chile. It's a whole new telescope that will take a picture of the full sky every night. And that's going to be a huge data set, similar to what I showed you, but based on images. So those were spectra from DESI. Those little robots took a spectrum to get the redshifts. Rubin will give us images of a billion galaxies and allow us to look at the distortion of their shapes due to gravitational lensing, which will be a huge goldmine of information. Euclid was launched by the European Space Agency with buy-in from NASA and is already taking data similar to Rubin in its goal, but from space. So not this huge mirror. You can't put that in space, so it's a different regime. SphereX was developed at JPL and launched like last month or so, and will look at inflation and make a large map of the full sky from space, again, not the galaxy. And so then Roman, NASA will launch Roman, so we'll get these huge data sets coming in, so that's very exciting. And so I'll end with the digital twin idea, and that's the holy grail, but in the meantime, we will be needing your help to be able to run these simulations, store them, read them, and write them. So that being said, thank you.
Any questions for our speaker?
Can you help me understand why the field of view is 90 degrees from our perspective?
This one, it's a visualization thing, actually. We, just in building this up, we replicate the box 8 times periodically. So I only show the part that's unique. That's a trick that we use. It's actually the full. This is a 2D representation, actually, of an octant of the sky, of a slice from an octant. So it's the full sphere. This is a wedge from it.
Marcelo, I have a question about the 1 petabyte of data set. You know, how do you manage that? Do you have that on Sherlock all at once? Because I don't think, I mean, it's quite a lot of data. Or do you do you work with like parts of that?
Yeah. So we, when we run the simulation, we write to scratch. So that's currently the I/O. It's 5 to 10% of our total runtime. So we consider that negligible. We could probably do better. It writes, it runs on about, those simulations ran on 512 Sherlock processors, so 16 nodes, 32 processes per node. The code ran basically 1 MPI task per process, and each one wrote to a separate file. So pretty straightforward parallelism. Things got, the write bandwidth got slower towards the end of the simulation, but that's just due to load balancing and synchronization issues on our side. And then that was the staging area, and then we move it to Oak for long-term storage, and then so we move back from Oak to Scratch for the analysis. So we do some staging back and forth, and so that happens quite frequently, and it's gonna, there's a few grad students working with this data, and so that's gonna be, I anticipate that's gonna be happening quite a bit. I saw somewhere.
Other questions for Marcelo?
Let's thank our speaker. Thank you very much.
Thank you.